All right. Hi, everybody. Hi, Jonathan. So today it's my pleasure to welcome Jonathan Ragan-Kelley, who's going to be presenting some work on some of his latest work. So Jonathan is the Esther and Harold E. Edgerton Assistant Professor of Electrical Engineering and Computer Science at MIT, and also an Assistant Professor of Electrical Engineering and Computer Science at UC Berkeley. He was previously a postdoc in computer science at Stanford, where he worked with Pat Hanrahan, and he spent a year as a visiting researcher at Google. His work focuses on high efficiency computer graphics at the intersection of graphics with systems, architecture, and compilers. And so Jonathan is going to be talking about his work exactly about that, organizing computation for high performance graphics and visual computing. And with that, please take it away, Jonathan.
Great, thanks. Hi, everybody. It's still weird giving talks into the ether, but I'm excited for this opportunity. So thanks, Emery, for having me, and thanks, everybody, for coming. This is a bit of a tour of some kind of key themes and ideas woven throughout the research that my group and I have done. And broadly, my research is about building systems for processing and learning about visual data. And I think this is a great area for systems research because visual data is central to most of the ways that we use computers today. Not just in the things you might normally think of like games, movies, and cameras, but also in everything from robots and self-driving cars to how we map the world to things like 3D printing, science, and medicine. But as successful as it is, visual computing has an almost unlimited demand for more performance and efficiency. So in rendering, for example, even using the same GPU as a PC game, a movie frame is still 6 orders of magnitude from real time. On the internet, basically all the biggest data is visual. So by 2015 even, YouTube was already ingesting 400 hours of new video every minute. But even that's just a trickle in the sea of active cameras in the world today, from medical scanners to smartphones to gigapixel telescopes. So we're developing powerful techniques to analyze all this data, but they're really expensive. So running one state-of-the-art object detector can take a large GPU just to process sub-VGA resolution video in real time. And while hardware has been getting more efficient for deep learning, the models have been getting more expensive at an even faster rate. So you might have seen this graph from OpenAI tracking the amount of compute invested in training state-of-the-art models from 2012 to 2018, but I think it's terrifying. So on the y-axis here, that's a log scale of compute. So in the 6 years from AlexNet to AlphaGo 0, there was a 5 order of magnitude increase in compute for training. And things like GPT-3 have kept this going even further over the last couple of years. Now, in general purpose computing, I think a combination of new languages, libraries, and systems have driven programmer productivity through the roof over the last few decades. But the sort of high performance implementations that visual computing problems need, I'd argue are harder than ever to build today. So to take one industrial example, a recent algorithm added to Photoshop a few years ago is relatively easy to describe in maybe a couple hundred lines of code. But to get it into production, one of the best engineers at the company had to spend 3 months re-implementing and optimizing it. And the end result here does the same exact computation an order of magnitude faster, which is great. But to get there, it needs code that's at least an order of magnitude more complex. And my group's research is largely about making this easier. So my group and I build languages, systems, and architectures and algorithms for these kinds of problems in visual computing. So specifically, I've worked on high performance image processing for computational photography and vision, 3D graphics systems from offline and real-time rendering to simulation and 3D printing, and most recently at the interface of machine learning and systems. And this includes both application of machine learning to optimize systems and new programming systems that broaden where we can apply machine learning, especially for vision and graphics. So throughout this work, I'm going to show that I think the real key challenge is to reorganize or restructure computations and data. That our ability to do that is deeply connected to the dependencies in a given problem. And that if we want to make progress, the key insight is to use domain knowledge to define abstractions that structure the possible dependencies in organizations. And then I'll show that by changing how we build systems from applications all the way down to hardware using this idea, we can enable radically simpler code and more efficient systems and hardware, even in the twilight of Moore's law. Okay. So what determines the performance and efficiency of apps like I've been talking about? So it often seems like performance optimization is about, low-level hacks and tricks, but the big issues are actually really fundamental. So first, we can just do less work. Computation takes energy and time, and we can be faster and more efficient by doing less. And second, we can do more things at once and exploit parallelism. Now, superficially, this might seem easy. All the applications I've talked about are enormously data parallel. And it's actually the fact that we have millions of pixels, objects, or neurons that makes us care about performance in the first place. The real challenge is that these millions of data parallel computations aren't independent. So they have to be able to communicate with each other. But it turns out that the same hardware trends that pushed us from one to many cores have also made communication and data movement dominate the cost of computation. So by communication, I don't even mean over networks. I mean inside a computer or even inside each chip. It just turns out that the simple physics of the way that we build computers mean that storing and moving values is literally orders of magnitude more expensive than computing them in the first place today. And as a result, locality, or moving data around as little as possible, is often the critical issue in modern systems. So because of this, it can often be most efficient to make sometimes surprising trade-offs, like redundantly recomputing values used in multiple places instead of storing and reloading them from memory. Okay, now, given these factors, how can we understand the performance of a system? We usually think of it in terms of two main layers that we're working with. So we have the hardware and then the program that we're running on it. But the key factors of locality, parallelism, and the amount of work that we do depend heavily on exactly how a computation is mapped to the hardware. So a key message I want you to take away from this talk is that because of this, you should often think of the program actually as two separate concerns. What I'm going to call the algorithm, or the fundamental operations that need to be performed, and then the organization of that computation, including where and when those operations are performed and where their results are stored and loaded. Okay, so what do I actually mean by the organization of computation here? Let's look at a simple example. So in lots of applications, we can think of the fundamental computation as some kind of a data parallel pipeline. So we have a graph of some major stages or kernels, and then we have some data being produced and consumed by each stage. Now, these data could be anything. So these could be pixels in an image processing pipeline, triangles in a 3D renderer, finite elements in a simulation, or activations in a deep neural network. In all these cases, the basic idea is the same. Now, how can we organize the computation of this pipeline? So if we zoom in and just think about two stages, we're computing a bunch of values in each stage. So we actually have lots of choices about where and when we compute and store each value. So one obvious thing we can often do is perform the computation what I call breadth first. So for each stage, we compute every value before moving on to the next. So in a 3D graphics pipeline, for example, this could be rasterizing every triangle before shading. And this is trivially parallel, but we have to have somewhere to keep all the results. So it requires storing them in a large memory. And we can immediately see then that this throws away any potential locality between the two stages. So by the time we get around to computing the second stage, all of its inputs have been stored far away. So we have to load them all back in order to compute it. So with locality in mind, it sort of seems like we'd want to interleave the computation of individual items in each stage in more of a depth first kind of order instead. So maybe we rasterize and immediately shade each triangle before moving on to the next. So if we eagerly feed values down the pipeline as soon as they're computed, then we could keep them in small nearby memory, like maybe caches or registers, where they're a lot cheaper to access. But importantly, in order to understand how we might actually do that, we need to break open the computations within each stage and look at the dependencies between them. So the dependencies among different computations can overlap or be irregular. So in 3D graphics, to continue that example, each piece of geometry might cover 0, 1, or 1,000,000 different pixels and might collide with any other piece of geometry in a simulation. And the pattern of these dependencies, or what you might call the sparsity structure of a whole computation, determines the set of possible organizations. So for example, we obviously can't compute values before we have their inputs. And it also determines the impact of each organization that each organization is going to have on parallelism and locality. But if we know the fine-grained dependencies, in this case, we could choose to interleave smaller chunks of each stage instead of the whole thing. So for each stage, we produce only a small chunk of values before passing them down to compute the corresponding chunk of the next stage. And we can get better locality by making the chunks small, or more data parallelism by making them bigger. We can also change or break the dependencies by recomputing values used in multiple places instead of storing them longer and then reloading them from memory. So here we might split the computation of chunks across, say, multiple processing cores. This might mean splitting up rasterization based on what part of the screen a triangle covers, for example. And then we can have each core compute its own copy of any shared values, avoiding any communication or synchronization. So given a computation, these are some of the kinds of ways we can reorganize it to be most efficient. But understanding all the dependencies and all the possible organizations gets really non-trivial when we zoom out and consider the whole graph of millions of operations across every stage. So if we want to do this systematically or automatically, how can we even begin to enumerate all the possible organizations? How can we know what organizations are safe when things like precise dependence analysis are undecidable? And even if we know something's safe, how do we know if it's going to be a good idea, given that the forces driving performance are often in tension with each other? So people have tried to build auto-parallelizing compilers for decades, but I think finding the best choice among an arbitrary set of possible organizations for fully general programs is probably just intractable. So today, it often still has to be done by hand at enormous cost by human experts. So looking back at the Adobe code I mentioned earlier, the optimized implementation does the exact same computation as the reference, it's just been organized differently. And it was finding that organization that took 3 months of work in this case. So using a traditional language, each of these organizations had to, each different organization had to globally restructure all the code, mashing together hundreds of loops in different ways. And because of stuff like this, not only is this kind of optimization, painful and expensive, but it also breaks the modularity of the resulting components. Now, the unifying theme of my research is figuring out how to make systems which can effectively organize computation for high efficiency. And the key intellectual challenge in general is figuring out how to structure the dependencies in possible organizations for the specific characteristics of particular applications. So instead of trying to make sense of an arbitrary mess of fine-grained computations that can be run in any order, I focus on using domain knowledge to abstract patterns in the dependency structure of important computations. That then makes it tractable to model, understand, and manipulate the critical dependencies. And then by defining a structured space of possible organizations, that's the key to being able to describe, transform, and automatically optimize the implementation. Okay, so my group and I have used this approach in a bunch of different areas of visual computing and at several different layers of the stack. And I want to talk for a few minutes about how it drove our work over the last 8 years on Halide. So Halide's a programming language for dense, regular data parallel computations. Think of things like image processing and deep learning. And it's built around the idea of explicitly decoupling an algorithm from the organization of its computation. So in Halide, one half of a program, what we call the algorithm, defines what values are computed for each pipeline stage and their dependencies, while the other half, what we call a schedule, defines a structured space of choices for where and when they're computed and how to organize the computation. So that makes it easy for the programmer to write and compose algorithms with lots of unnecessary details stripped away. It makes it easier for either a programmer or a compiler to specify and explore possible optimizations. And then it leaves the compiler to do the complex but deterministic work of generating code that implements the algorithm given a schedule. So to start out, algorithms are written in a declarative functional style. So once we strip out the concerns of scheduling, the algorithm is a series of functions from pixel coordinates to expressions giving the values of those coordinates. These functions don't have any side effects. They can be evaluated anywhere in an infinite domain, and the required region of each stage is just inferred by the compiler. The execution order and storage are not specified by the algorithm, so these points can be evaluated in any order. The results can be cached, duplicated, thrown away, or recomputed without changing the meaning. And the code looks roughly like you see here on the bottom for a simple two-stage pipeline. So in this case, the first stage F is defined at any point x, y as a nonlinearity applied to the input. And then G at any point is a convolution of 3 points in F. So notice again that there are no loops, bounds, or mutable memory buffers here, just a declarative specification of how to compute any point in any stage, including the ability to identify all their fine-grained dependencies. Now, the specific scope of this programming model is what lets us understand dependencies and have lots of flexibility in scheduling. So first, it's only modeling functions over regular arrays, what you might call tensors. Second, it focuses on feed-forward pipelines. This is a good fit for imaging and vision, but not for everything. It can express limited recursion and iteration, but basically only countable loops. And that means it's actually not Turing complete, although a major current project of ours is generalizing this in a way that keeps the analysis tractable in practice. Okay, so we had this nice constrained functional model for expressing imaging and array algorithms. Now, how can we organize it? And what we did is create a new language as part of Halide. It defines a structured space of key choices and can concisely describe most critical optimizations. So in Halide, a schedule breaks down the organization of computation in pipelines like this into two key decisions for each stage. So first, in what order should we compute its values? So remember, we're computing whole arrays for each of these functions. So in what order should we compute the points in each array? Second, when should we compute pieces of its inputs, or what granularity? And that's going to define the interleaving of evaluation between producers and consumers in the pipeline, which controls locality. And this is the core model that we use to describe the space of ways a computation can be organized. So different choices about the order within and across stages can describe all the types of organization I showed earlier and more. And composing these choices in different ways for different stages spans the space of trade-offs globally for a whole pipeline. Okay, so the scheduling model within each stage is relatively simple. So you can apply all the classic transformations of perfect loop nests like splitting, reordering, tiling, vectorizing, that kind of thing. But the way that we model the global trade-offs, the things across stages, I think is the most fundamental and unique idea in Halide's design. We do that by controlling the granularity at which the storage and computation of each stage gets interleaved. So the granularity with which we interleave computation determines how soon you use values after you compute them. So on this axis, fine-grained interleaving provides high temporal locality, quickly switching back and forth between computing and consuming values. Well, coarse-grained interleaving provides less locality, computing lots of values before using any of them. On the other axis, the storage granularity basically determines how long we hold on to values for potential reuse. So fine-grained storage only keeps values for a short time before throwing them away, which can cause redundant computation if they're needed again later. Well, coarse-grained storage keeps values around longer in bigger buffers to capture more potential reuse. So using the organizations we explored a little bit at the beginning, breadth-first execution here avoids any redundant work by interleaving computation and storage at the coarsest granularity. But as we saw at the start, this sacrifices locality. So in our scheduling language, this interleaving choice is described by the simple code on the right, which I'm not going to describe, but gives you a little bit of a taste of how this is encoded. At the other extreme, full depth-first fusion interleaves the storage and computation of the two stages at really fine granularity. And it breaks the dependencies between shared values. So this maximizes locality, but it produces potentially lots of redundant work where the dependencies might overlap. By setting the storage granularity to the coarsest level, while still interleaving the computation at the finest, we get what I call a sliding window pattern. So this has high locality and does no redundant work, but importantly, doing it synchronizes the iteration of the two stages, which limits the available parallelism. And we can also trade off along these axes from here. So tile level fusion, for example, trades off between locality and redundant computation, depending on the granularity of the tiles that are interleaved. Or starting from a sliding window schedule, we can coarsen the compute interleaving to regain some fine-grained parallelism within the enlarged windows at the expense of some locality. We can regain coarse-grained parallelism by performing sliding windows within multiple parallel tiles, introducing a bit of redundant work on the tile boundaries. Or we can combine all these strategies to span the entire interior of the trade-off space. So even for a trivial two-stage pipeline, we can express a nearly infinite range of choices in how to organize the computation. And I don't know how well this is going to come across on Zoom, but this is a little cartoon of what they actually look like running. So different strategies here are going to be best depending on the exact algorithms that we're using, the structure of the surrounding pipeline, and how they interact with the underlying hardware. And the difference between them can easily be more than an order of magnitude in performance and efficiency. And that's just for two stages. So a more realistic pipeline looks something like this. So local Laplacian filters has about 100 stages in a complex graph. And it gives us lots of choices about the organization and degree of fusion at each of dozens of stages. So each plausible strategy can mean a totally different set of dozens of kernels or loop nests, completely restructuring all of our code. And the difference between two plausible strategies could be an order of magnitude in efficiency. And to put this in concrete perspective, this is that algorithm we saw earlier from Photoshop. So remember, Adobe's version was written by one of their best engineers in about 1,500 lines of C++ and intrinsics. And it took 3 months to implement and optimize for parallelism and locality. In comparison, a few years back, he and I took a single day to rewrite it in Halide and integrate it into Photoshop. It took 60 lines of code and ran twice as fast as their version on the same machine. And this is the kind of result we've often seen with Halide, but how did we beat this expert tuned code? I usually don't trust people when they take some speed of light thing and then say they beat it by a whole bunch. In this case, the win came mostly from interleaving stages differently and breaking some dependencies to trade redundant computation for better locality. But we didn't just make a few extra optimizations. We had to fuse and schedule each of the 100 stages differently to globally balance parallelism, locality, and the total amount of work over the whole pipeline. And basically the issue here is that the best organization of computation was just too hard for the original developer to find. So he stopped after 3 months of rewriting and optimizing for a specific machine. But with Halide, it was orders of magnitude easier to globally reorganize the computation. And as a result, we were able to try more stuff very quickly and ultimately find something more efficient overall in an afternoon. And at the same time, Adobe's been very interested for years in using GPUs in these products, but they can't afford to rewrite these thousands of lines of code for each new accelerator. But in just a few minutes, just by changing the Halide schedule, we also generated a GPU version that was 10 times faster still. And importantly, this wasn't just a translation. The best schedules on different architectures organize the computation in totally different ways. And today, different versions of this code are also in Instagram and Google's HDR+, using different schedules to target a wide range of different accelerators. Okay, so that's Halide. To recap, the big idea here was to explicitly decouple the definition of the algorithm from the organization of its computation, and then to define a structured language of key scheduling choices. And the end result are simpler programs that often run faster than prior hand-tuned code, while giving composable and portable components that can scale from embedded DSPs up to supercomputers. And it's being used pretty heavily in the real world today. So it's in Photoshop and Instagram and all kinds of other things, from every Android phone to to most of the videos processed by YouTube. So in YouTube alone, I believe it accounts for a non-trivial percentage of all of Google's server CPU cycles worldwide. And the performance improvement it brought eliminated megawatts of data center capacity. So Halid's also at the core of some of the new deep learning compilers. And overall, there's Halide code running in production on billions of devices, including almost all the phones in your pockets right now. And most of Google's Pixel phones even include a dedicated accelerator chip they developed specifically to run Halide for things like the night sight mode in their camera. Okay, so popping back up, this fundamental idea of using domain-specific structure to master dependencies and reorganize computation, it's been at the core of my work on Halide, but it's also led to insights and contributions in a bunch of other areas. So now I first want to move down the stack and talk about hardware for a little bit. So Halide helps us get the most out of a given processor, but for lots of real-time imaging and vision tasks, even that's not enough. And the problem, in some sense, if you want to call it that, is that modern image sensors are amazing. So my iPhone has 3 12-megapixel cameras, each of which pumps out close to a gigapixel per second of data. So for things like real-time tracking and robots in VR, or even just taking better pictures with your smartphone, we'd like to be able to drink from that fire hose and still be able to do some serious computation on every pixel. And now, those of you who know MIT very well know that we do like to drink from fire hoses, but more seriously, if we want to do just 1,000 ops per pixel at these kinds of data rates, we need teraops per second of compute. And to do it in your phone or headset, it needs to take usually less than a watt of power. Now, on its face, this sounds terrifying. So even at its theoretical peak, a mobile CPU can often only deliver about 25 gigaops per watt. A mobile GPU tops out at best maybe 10 times higher than that, but it's still an order of magnitude short. But if you remember the fundamental costs of computation, this seems like it might actually be possible. So we can do raw math at teraops per watt in modern hardware. The issue is that we just can't afford to move the data very much. And from this perspective, basically the only option is to take a radical approach and to implement the whole computation in a single streaming pass over the data. So if we can avoid going back and forth to memory and keep the on-chip data flow local from one operation to the next, then we can spend our energy on compute instead of on data movement. But this requires heavily restricting the structure of possible dependencies and using a specific structure to organize the computational logic in space and time. Your cell phone includes a dedicated image signal processor, or ISP, that uses an approach exactly like this to deliver teraops of computation in a fraction of a watt. So let's look for a second at how these architectures work. So we can start with a simple operation like black level. It takes in 1 pixel, adjusts its black level, and produces 1 pixel out. We can build this in hardware. So we have wires for the input and output pixels and all of the math packed together in between. We can connect it to our camera sensor and connect the output to DRAM where it'll write its output image. And then this basically becomes an extremely simple camera ISP and processes 1 pixel per clock cycle. And we can easily add any number of additional blocks that also process 1 pixel at a time to build a pipeline of operations. So if we compose 1,000 trivial ops this way and run it at a gigahertz, we'd already have our teraops circuit. But we obviously need to be able to do more than just pointwise operations. You think about functions like demosaic or stereo matching. These kinds of computations have to read a whole neighborhood of pixels for each output. And ISPs deal with stencil functions like this by buffering intermediate values and delaying computation until the whole input window is available. So if we have some function f feeding into a stencil function g, we have to think about where each of them is in its logical progression through the image. So if we want to compute g here, for example, we need to consume this window of f. Now, data flows through in scan line order coming out of our sensor. So we need to wait until enough lines of the prior stage have been computed to cover the stencil. Then as soon as they have, they can be consumed to compute the corresponding pixel of this next stage G. Now, ISPs hold these intermediates in a small local circular buffer, often called a line buffer, that's just big enough to hold the required values. But stepping back to the chip that we're building, we can add line buffers to our pipeline anywhere we need to support stencil operators. And that's the basic architecture of current hardware image processors. They're able to be so efficient because they keep all intermediate values local and never have to touch large memories. Now the problem, I just said how your phone already solves this problem, but the problem is that designing advanced algorithms directly into hardware like this is really difficult and expensive. So Apple's camera team has on the order of 1,000 engineers, last I heard, which was actually a number of years ago, just to turn out one major design per year. So I'd argue this is another case where current tools conflate the core algorithms in their organization. In this case, all the way down to physical implementation and circuits. So we have to take our nice high-level imaging algorithms and manually translate them to a register transfer level specification of every detail of the hardware logic we want to build. Of course, automatically synthesizing efficient hardware like this directly from high-level languages has been a holy grail for decades. But just like automatically optimizing software code, it's proven intractable for general programs. But applying the philosophy I've been arguing for, using this understanding of the domain to define a structured space of computations and organizations, some colleagues at Stanford and I defined a new domain-specific language for hardware synthesis called Darkroom. So it abstracts and generalizes the architecture of ISPs into what we call line buffered pipelines. Now, a line buffered pipeline is a specialized class of synchronous data flow. So it's a DAG of stages where each stage is a pure function of a fixed size window of inputs. And again, the key issue is the structure of the dependencies. These highly efficient hardware implementations are only possible given bounded dependencies between stages. So we built the language around that constraint. So you can only write programs in Darkroom that conform to that constraint. But it's flexible and expressive enough to implement lots of useful imaging and vision pipelines in just, usually like dozens of lines of code. So along with this structured dependence patterns, we also showed that line buffer pipelines have a highly structured space of possible organizations. And even better, we showed how you can directly solve for the optimal buffer minimizing design as a polynomial time integer linear program. So in just a couple of seconds, our compiler can spit out an optimized structural Verilog implementation of a given high-level algorithm that uses the minimum possible amount of interstage buffering. And the results are competitive with traditional hand-optimized hardware. So post, place, and route in a admittedly now vintage 45 nanometer process, a couple dozen lines of code gives gigapixel per second throughput in a couple hundred milliwatts and a fraction of a square millimeter of chip area for a range of different algorithms that we looked at. So we presented a series of papers at SIGGRAPH and elsewhere on this core idea, generalizing it to support multi-rate implementations and algorithms, targeting FPGAs, and ultimately unifying it back into Halide's language of schedules. All right, in another line of work, stepping beyond hardware, we've looked at legacy code. So you can do a lot, both in software and hardware, with the right domain-specific abstraction. That's what everything I've shown so far has been all about. But so far, we've been asking people to rewrite code in a new programming language to get those advantages. But you might ask, what about all the legacy code that's already out there in the world? Could we maybe extract structured dependencies and figure out how to reorganize their computation? If we're being particularly masochistic, could we maybe even do it from the binary alone? So in the general case, this is obviously impossible. But we found kind of amazingly that it was possible to reconstruct some image processing algorithms directly from optimized binaries by dynamically tracing their execution and analyzing thousands of iterations to infer the dependent structure. So once we'd done that, we were literally able to infer the algorithms underlying real Photoshop code in a shipping binary and lift it all the way to Halide code. Recompiling that with a new organization, we showed it was possible to replace the original code right inside the running copy of Photoshop and get better performance on new machines. Last year, we released a newer sound static version of this approach in collaboration with Alvin Chung's group in Adobe, and it's based on program synthesis. So using this, we're now automatically translating most of Photoshop's core blending and low-level filter libraries. This is code that has a history going back more than 30 years to the late 80s. And its port to Halide is at the core of Adobe's effort to bring full Photoshop to iPad. All right. So the core approach I've argued for applies at many levels in image processing. And that's what we've talked about so far. But now I want to give a really quick taste for how it's also really powerful in other areas like 3D graphics. So in rendering, I found that the biggest key is often to reorganize computation for reuse. So for example, early in my career, I applied this idea to build an interactive preview system for special effects and animation. The problem here is that it takes hours to render a preview each time the artist makes an edit. But most of that work is redundant. So if you imagine that I'm only changing the lighting parameters, a lot of the rendering computation stays the same. So we built a compiler to analyze the dependence of the rendering on what the artist is actually changing at any given time. It automatically reorganizes the computation to do most of it in a pre-process that only happens once, and then maps just the dynamic parts to a GPU. The end result runs 10,000 times faster, so it's interactive instead of taking hours per frame, which is really useful for artist productivity. So this system was in production at ILM for 6 years, where it was used on almost 20 movies and was a finalist for an Academy Technical Achievement Award. In real-time graphics pipelines, shading is often the dominant cost. So effects like motion blur require lots of visibility samples, but shading on a given surface element doesn't change much. So we rethought the architecture of the real-time graphics pipeline to more efficiently render effects like these. And the key idea was tracking complex dependencies, this time in hardware, to reduce redundant shading. And our reorganization reduced total rendering costs by an order of magnitude on real games. So since then, NVIDIA has adapted this for their latest generations of GPUs, and these ideas have influenced most real-time game engines out there today. Now, another application that raises interesting systems challenges is 3D printing. So a big challenge in multi-material 3D printing is the data size. You can print up to gigavoxels per cubic inch at modern printer resolutions. So to address this, together with the computational fabrication group at MIT, we helped build a system that represents the input to a 3D printer, not as a static model, but instead as a procedural program. We designed it to be able to express any volumetric output while structuring the computation for efficient organization so that it can be streamed for locality and parallelized for scalability. Now, lots of applications in areas like physical simulation, optimization, and inverse problems also use sparse and irregular data structures. So in these areas, the dependencies literally correspond to mathematical notions of sparsity. And here we've worked on a series of domain-specific languages where we've shown how to capture structured sparsity in programs, perform high-level mathematical transformations, and compile simple code directly to efficient matrix-free organizations. And my group is continuing to push on these areas today. Okay, so that's a little bit about how these ideas apply to 3D graphics. And I want to wrap up just by talking about how I think they're critical to making the most of machine learning too. And I specifically want to address two key contexts from our most recent work. The first, how can we use machine learning to optimize the performance of our systems? Can we automate the kind of performance engineering that traditionally needs human experts to do it by hand? And second, how can we broaden the applicability of machine learning techniques? And specifically, how can we use gradient-based optimization to make more general programs in some sense learnable? And how can we use learning systems in contexts where large deep networks are still just too expensive? And the structure of computation and its organization gives a powerful lens for both of these problems. So there's obviously lots of interest in applying machine learning to everything, including systems. But the sorts of performance engineering usually done by human experts requires precisely navigating very complex spaces of possible choices. And there's highly nonlinear behavior in how these choices impact performance. So the kind of structure I've been talking about, I think, is critical to leveraging learning in this context. And that's because it enables the combination of learning with powerful program analysis and search techniques, where each is insufficient on its own. So using this idea, we've been working on learning to automatically schedule arbitrary halide programs better than the best human experts. And we're also working on systems that broaden the scope of deep learning techniques and make it easier to achieve high performance. So by creating a programming language that's both automatically differentiable and efficient, we can, on the one hand, use learning techniques to better optimize the internal parameters of traditional programs. And on the other, build new neural network layer architectures, or even entire networks, with a more general computational model. So in some sense, we're both bringing a more general computational model to deep learning and bringing deep learning to more general programs. All right, so first, about optimizing programs. I don't think anybody who's done much performance work would disagree that performance engineering is hard. So traditional heuristic-based compiler optimizations are great, but they aren't nearly as good as humans at the sort of large-scale reorganization that gives order of magnitude wins. So lots of people in recent years have been hoping that learning is going to help compilers do a lot better. But I think there's still a key question around how we even can learn to optimize programs. And with Halide, we defined a structured language of schedules that describes most important optimizations. And we also have a growing mass of real expert-tuned code. So the first thing you might imagine doing is taking kind of an NLP approach and training a system to directly predict fast schedules for a given algorithm. But I actually think this is throwing out the baby with the bathwater. The space of schedules and their performance characteristics is incredibly complex. That's why it's difficult to optimize performance, but it's also highly structured. Instead, I think the right approach here is to combine the strengths of structured search algorithms from classical AI with all the program analyses we know how to do in compilers and modern learning techniques. Then we can focus the learning on predicting the best policy to guide the search, given everything that we can infer about the program from classical analyses. So you can think of this sort of like AlphaGo, but for optimizing programs. And this is exactly what we've done over the last couple of years in Halide. And our first paper on this was at SIGGRAPH last year. So the big idea is that we train a small deep model to predict the performance of thousands of random programs and schedules on a target machine. And then we can use that model to guide either a beam search or to guide a beam search over a structured enumeration of possible schedules. So we can either find a schedule in a few seconds directly from this search. You can think of like -03 in a compiler, just looks at the program and makes good decisions about how to optimize it. Or if we have more time and the ability to take benchmarks, we can import and sample the space of schedules that are favored by the model, benchmark the top results, and add a final layer of auto-tuning. And that's useful if we have a few minutes to a few hours to wait for better results. And just to summarize very quickly, the punchline is that this is working really well. So this is the first automatic algorithm that consistently outperforms human experts on a wide range of real image processing, graphics, and learning workloads that we target in Halide. So across quite diverse benchmark suite with a few dozen programs, it essentially matches human experts in that instant -03 mode, and it outperforms them by 40% on average, given about an hour of auto-tuning time. And sometimes it's an order of magnitude faster. Zooming in and looking at one production serving workload for my co-authors at Facebook, it's able to match or exceed the hand-tuned ConvNet implementations of all the major ML frameworks. And it does this, importantly, from scratch with no human involvement. So unlike most of the popular deep learning focused compilers, it's fully automatic all the way from arbitrary high-level Halide code. There's no assembly kernels, assembly template kernels for the inner convolutions or matrix multiplies, and the system has no special knowledge of deep learning. Now, on the other side, starting from Halide, we've been building a fully differentiable programming language. So modern ML frameworks like PyTorch and TensorFlow are great for traditional deep learning. As long as what you want to do is well described by the standard layers they provide, they automatically give you both efficient GPU implementations and derivatives for gradient-based optimization. But I think the frontier of deep learning often involves extending traditional architectures with new differentiable operators. And that can be the key to capture problem-specific structure and make learning practical and efficient for new problems. And the fixed library of coarse-grained operators in traditional frameworks makes it really difficult or impossible to express many new operators. And the result is also, when you can do it, is often fundamentally inefficient, since they can't reorganize computation across operator kernels. The only alternative people have usually is to hand-derive gradients and manually implement it all in CUDA. But by balancing generality and structure, our differentiable programming language is, on the one hand, it winds up being faster and more general than PyTorch or TensorFlow for defining novel architectures like this. And it's orders of magnitude easier than handwriting CUDA. So that makes it a lot easier to define novel architectures for deep learning. But more surprisingly, and I think more interestingly, we've also shown how you can use it to take traditional programs, learn more optimal parameters, and get deep learning level results. So for example, AHD is the state-of-the-art classical demosaicing algorithm, like the one still used in your camera today. But it's been surpassed dramatically by deep methods in the last few years. But just by taking the same loss function and training data used on those deep methods and using them to resolve for optimal parameters of the classical algorithm, we were able to dramatically improve its performance, approaching the best deep models. But importantly, this learned classical program uses literally 1,000 times less compute and data than the convnets. And once the parameters of the whole algorithm are automatically learned, it's also easy to explore a whole space of variance. So for example, we showed that you could throw in things like larger or smaller filters in different places to trade off performance and quality. And doing this is relatively effortless with the differentiable programming language. So we're blurring the boundary between deep learning and more general programming. Looking forward, I think this points towards a whole new way to approach learning for efficient inference, especially for performance critical tasks like high resolution real-time imaging and video. In my group over the last year, we've been starting to investigate learning to solve these tasks by combining program synthesis over this broader space of differentiable programs with gradient-based optimization of those programs' parameters. So instead of relying only on the massive overparameterization of traditional deep networks, the resulting programs combine algorithmic structure with parameter tuning to solve tasks with potentially orders of magnitude less compute and weight data, like I just showed for demosaicing. And we're also starting to think about unifying Halide's decoupled scheduling model for arrays and everything that we built around it with more general data structures using a relational perspective. And finally, I think there's major systems problems in realizing the potential of data center computing for vision and graphics. So I'm excited about some projects we've been working on to easily program large data centers to do large scale linear algebra. And ways we've been using this to explore the limits of kernel methods at deep learning scale. All right, finally, I just want to say that all this work has only been possible because I've been lucky to have an incredible wealth of amazing students and collaborators. And with that, thanks.
All right, thanks, Jonathan. So you'll get to hear me applauding. I'm the proxy for everybody else out there. So great talk, very interesting stuff. We have a few questions. I'm going to go ahead and start with this one from Elliot Moss. To what extent is the exploration of schedules for a given hardware target automated? Does this all have to be adjusted by hand? I feel like I know the answer to this question, but go ahead.
Yeah, I'm not sure how early that came up.
It was early-ish.
Yeah, because I got to searching space automatically later on. But yeah, that's a great question. So the answer, I think, is that this decoupling of algorithms from their organization is useful both for humans, when you want human performance engineers to be able to have control. One issue with traditional automatic optimization techniques is that they're great when they work, but the moment they fail in some part of your program, you basically have to completely give up automatic optimization. Having a productive way of taking control without dropping all the way to low-level code is really powerful and really productive for the people who want control and have the skills to use it. But I think the same structured space that lets humans concisely reason about their choices is also a really natural space to search over. And I touched on our most recent work in that area. We've been extending this to other accelerator architectures and other things more recently, but we've been working for half a decade on searching that space automatically in different ways too. So I think the basic idea of trying to design this decoupling into the language and define a clearly structured space of choices, in my view, is the right way of doing both things.
Sounds good. So let's see. Let me go ahead and ask a question of my own. Somebody is typing. So you talked about extending this work to cover sort of structured data, things that aren't in arrays. So I wonder what your thoughts are on that, only because of sort of well-known performance discontinuities that arise in these settings. You know, there's work of mine and work by Todd Mitkowicz et al. That showed how brittle performance can be just because of layout. And so if you have these, you know, you have a dynamic data structure, and depending on what got allocated when, where things end up, you can get these gigantic swings in performance. So I was curious to hear what your thoughts are about that.
Yeah, so I mean, it's worth pointing out that, so a lot of what I talked about, or at least the stuff I talked about in the most detail, often deals with relatively static data and control flow. That's very true in the imaging and traditional ML, modern traditional ML domains. It's less true in some of the things I glossed over, like physical simulation, 3D printing, 3D rendering, and so on. Those are contexts where dealing carefully with dynamism and irregularity in key parts of the pipelines is actually really important. But I'd point out that even for regular stuff, there's extreme brittleness in a bunch of parts of the stack that we depend on. So one thing we run into when like learning to predict the performance of different scheduling choices, for example, is that we're sitting on top. We have a fairly hefty compiler of our own that's relatively predictable in what it does, but it does have a few parts that are kind of heuristic and harder to predict. Like it depends heavily on automatically inferring the bounds of intermediate buffers and loops, and that bounds inference process depends on a complicated algebraic simplification engine to do a good job, like simplifying and stripping down the code so that you're not evaluating really complicated index expressions at runtime. So whether or not that succeeds for a particular configuration can make a big difference in performance. And a level below that, we're sitting on top of LLVM and often like NVIDIA's PTX compiler, where even things like register allocation, you can roughly reason about them in a lot of contexts, but they're out of our control and are handled by a complex black box. So we regularly find that one of the big reasons why I mentioned that we can do pretty well in this, what I call the -03 mode, where you just use the model to directly make a choice, but you can often do a lot better with auto tuning. I think there's two reasons for that. One is that we can, the model's trained on a whole bunch of generic data, and we can fine tune it on the results of a specific program as we take more samples. So we can adapt our ability to search to the characteristics of that particular program, which helps a bit. But a big one is actually just that the performance characteristics of the entire stack we're sitting on top of are broadly predictable, but have nasty brittle cliffs all over the place. And so simply being able to generate 10 samples and pick which one is empirically the best, 10 plausible samples, according to the cost model, and pick which one is empirically the best, is really important for dealing with that kind of brittleness. So I think in general, the more the end-to-end performance depends on things that can't be easily modeled or predicted, which can both be just very complicated system components, or could be dynamism in the workload itself. I think driving the process based on actual observation of real execution is really important. And I think you see that in like the databases world, like profiling the real data is very important to be able to do more powerful optimizations effectively in query planning, for example. And I would expect the exact same thing in those settings.
Okay, sounds good. I actually still think there's going to be, well, so it depends on how data dependent these layouts are, right? So if you're in a space where you're doing your auto tuning and you've auto-tuned over some sort of training set, if you will. And then if somebody gives you something that is some tree that's sort of different in shape than something you've observed, then God knows what'll happen.
Yeah,
so
absolutely.
That'll be interesting to cover.
Yeah, I think but I would argue that, I mean, that's a risk with human performance engineering also, right?
Absolutely.
Or writing arbitrary low-level code. So yeah, it's,
right.
I think these are just challenges with optimizing stuff that has complex dynamic behavior.
Sure. Yeah, that's a good point.
But and maybe argue even more strongly for having a compiler and code generator and auto-tuning system in the loop, because you by the time you have all that, you've lowered the cost of re-optimizing for specific problem instances or specific cases by many orders of magnitude. You don't need a human to go back in and retune everything. It may be too expensive to do on the fly from second to second, but you have way more opportunity to adapt to many more narrow niches. The more automated the system is.
That makes sense. So I'm going to go ahead and ask another question of my own before I get a couple audience questions. So I know this is very difficult to quantify, but how hard do you think it is to program in Halide versus, I know it's clearly easier, well, one has to assume, than the manual process of writing CUDA code, which is a nightmare. I speak from personal pain. But how would you, would you put it, where would you put it on sort of a spectrum between naive programmer writing like the worst possible matrix multiply to the rock star programmer who is counting cycles?
So I think not surprisingly, with a two-part language, there's separate answers for the two parts. So I think the algorithm part of the language, for things that are a decent fit for the computational model, obviously one characteristic of being a somewhat restricted domain-specific language is that as you push up against the boundaries of what easily fits into the model, like at the very periphery, you start, you have to be very clever to play tricks and to contort your problem into something that still fits well, and then you fall off a cliff where there's stuff that you just can't reasonably express. I wouldn't want to implement like rebalancing a red-black tree in Halide, probably. But I think absent that, and absent the overhead of people already, novice programmers or domain programmers already being experts in a separate tool. If you normalize for experience with the tool, I think the Halide algorithm language we've actually found is quite easy to use for computational science, ML, image processing type people, and it actually simplifies code in a bunch of ways relative to traditional languages people use, because of ways that like boundary handling is abstracted and stuff like that. So you get to basically write everything from the perspective of one element, one element locally within each stage, and think about that. Orthogonally impose boundary conditions where you care about them, and all kinds of indexing math and stuff that gets really nasty and is a huge source of bugs, even if you're writing like NumPy code, largely goes away. So that's great. Writing schedules, by contrast, is very difficult. It's, I think the right way to put it is it's a metaprogramming power tool for advanced performance engineers. It's way more productive than handwriting CUDA for stuff that's in scope for what it can effectively do. But people who write optimized schedules are still, like looking at their assembly output and thinking about how I can slightly tweak this structure to get the particular opcodes I want to come out or whatever, or like hit the right register count. And I think the challenge, so one thing I'm interested in over the next few years is actually working on language design for this idea of scheduling languages. I think what we have in Halide is a very kind of, in some sense, naive and practical first crack that has a bunch of issues that a traditional PL lens could help clarify. So schedules, for example, algorithms are naturally highly modular and composable. Schedules fundamentally are about cross-cutting concerns and mashing stuff together to create the particular imperative structure you want. So abstraction and modularity in scheduling languages is something we basically haven't touched at all. It has a lot of the challenges of kind of aspect-oriented programming, because you're like reaching into a program and saying, I want to take this thing and or this class of thing and do stuff to it. And it has all the challenges of staged and higher order programming in terms of the difficulty of the mental model, and potentially better tools, you could imagine something like Proof General or something like that, that gives you, if for anybody who's familiar with Coq, that gives you like a live view of like the state of what you're manipulating while you're manipulating it. Because currently people writing schedules are like, normally when you write a program, you have to emulate the abstract computer in your head to think about what it's doing. When you're writing schedules, you're emulating an abstract computer, but that abstract computer is a compiler that's transforming an imperative looping program. And that's a somewhat challenging mental model, in truth.
Yeah.
So there's like some people for whom this works really, really well, but they're generally people who are very advanced performance engineers already.
Okay, great. So I'll move on to some audience questions. So you talked about lifting from x86 code, and I know that you've, I'm pretty sure that, well, certainly I've seen a paper on doing this for Fortran. The question is it possible to generate them automatically from existing C++ CUDA programs?
That's a great question. So Alvin had worked on, Alvin and another collaborator of mine, Shoaib Kamil, had worked on doing this for Fortran programs. We picked that thread up and extended it significantly in the paper I referenced from a year ago that's being used in Photoshop today for C++ and a wider class of computational patterns. I think CUDA is something I'm very interested in attacking in this way, where I think there's actually even more opportunity, because while but it's not something that I've done. I think Alvin and Maz, who's the student who led that work, have worked on CUDA a bit. I'm not sure the status of any of that work though at this point. I don't think anything's been published. We often think of CUDA programs being even hairier and nastier than average C++. I think they do impose some key structure that you can exploit, namely that programs have to be decomposed into kernels and being invoked over regular grids. And the data flow dependencies of buffers between those kernels are all made explicit, at least if you observe the execution of a graph of memcopy operations and kernel invocations. And well, a completely insane CUDA program that's using atomic operations to do fine-grained synchronization and using persistent threads and an arbitrarily complicated CUDA program, I think would be very difficult to try to abstract. The median CUDA program is often a much more straightforward set of data parallel kernels than that. And I actually think we might be able to do an even better job on that than on kind of a soup of C++ in Photoshop or OpenCV, which is the target of what we've done so far.
Sure, that makes sense.
Cautiously optimistic. But
yeah, I mean, I think leveraging the structure makes a lot of sense, and plus, yeah, C++ code can obviously be a total mess.
Yeah, C++ code often gets abstracted through many layers of, you have many layers of abstraction and templates and stuff that also get in the way that are, whereas the base structure of iteration spaces and raw buffers and stuff is often much more directly exposed in CUDA programs.
Right. Sounds good. So let's see. There's another question. Have you thought about extending the scheduling part of Halide to other problems? For example, scheduling for distributed model training or over multiple GPUs?
Great question. Yeah, so I would say, so I think the general idea of decoupled scheduling languages or user controllable scheduling languages is something that my group and I are thinking about in a bunch of different contexts. You can maybe kind of divide the world into the stuff that's roughly in scope for the Halide computational model and stuff that's further afield. So we're working often on separate DSLs for other computational patterns and data structures. Those are both things that I would say reasonably fit within the Halide model, but just haven't been addressed by the exact set of scheduling primitives and the current compiler and runtime stack. But they are, I think, insightfully, I actually think of those two being closely related because they both relate to, so both multi-GPU and distributed training settings are both basically about distributed memory setting. And that is something that a student of mine is thinking about right now.
Okay, great. Yeah, so let me ask a follow-up question, which is a very broad question. So, I mean, you've had tremendous success with Halide. I think it's it's amazing stuff, really, really terrific. And you've talked about extending it to different spaces. So, where do you feel there are fundamental limits beyond which you just cannot possibly imagine going? Are there, programming language? Well, just broadly, what are the kind of problems that you think you will eventually be able to reach, the ones that are going to be permanently out of reach and ones where you're not really sure?
Yeah, so I think, again, I would maybe draw a distinction. I probably oversimplified. It winds up seeming like everything I talked about is halide, and I feel like probably like half of everything is literally halide, and the other half is related ideas in other contexts. And so I would again maybe draw a distinction between where the type of philosophy of so I think of domain-specific languages, particularly high-performance domain-specific languages, often aren't. I think domain-specific is often a misnomer. They're often much more data structure and computation pattern specific. And on kind of the algorithm definition side, the key thing is usually having structured ways of understanding aggregate data structures and aggregate, like collection-oriented operations on those aggregate data structures. Halide proper, halide TM, the actual compiler and language, is pretty heavily focused on dense regular arrays. And we have a line of work, a language called Tai Chi, that basically takes very similar ideas working on grids, but allows those grids to be spatially sparse, which is useful for some physical simulation problems. But I think once you get to like graph structured data, meshes, like irregular tetrahedral meshes in simulation, which we've done some work on in other settings, halide proper, it's difficult to imagine halide proper directly generalizing to that kind of thing. But I think the idea of decoupled scheduling language combined with some powerful abstract collection types and collection-oriented operators, where the scheduling language is basically responsible for defining the concrete implementation choices of those abstract data structures and operators, is a pretty broadly applicable philosophy to lots of things that we have any structured way of thinking about. And then there's just a question of how much you can unify under one roof. And I think the farthest we're pushing with unification actually is with a new language or IR that we've been working on in my group over the last year and a half. That's less production focused than halide, but tries to get at its fundamental abstractions are tensors, but those depending on the class of indexing operations and stuff that you're allowed to use in those, it winds up unifying dense and sparse tensors and relations in a relatively clean way, where you can talk about subparts of the program where halide-like ideas are applicable and subparts where like taco type ideas would be applicable, and the interface between those things. So I think there are opportunities to push significantly farther, but doing that in a production language and compiler artifact is probably not the first place we'll do it, if that makes any sense. So halide's not going to be the first place these ideas get tied together. It's going to be stepping back to more, research PL fundamentals. And then hopefully those ideas will carry forward to future practical systems.
Right. Okay, cool. If one thing that would be useful actually that we can add as comments on the video, by the way, is links to some of the papers, since you had so many papers that you discussed.
Yeah, absolutely.
You can share those with me later. I'm sure that'll be useful to the audience. So let me just, there's two more questions if you have a little more time.
I have time, yeah.
Okay, so one is, can halide adapt to changes in the hardware paradigm? Something like processor in memory based accelerators.
I think by nature, paradigms are, it's difficult to think across paradigm boundaries. I think the philosophy of science people who popularized that word largely are talking about that. So it depends what you have in mind. I could talk concretely about farther afield ideas in the computer architecture world. I would say processing in memory, it heavily depends on what, it's not obvious to me what the mapping would be. It heavily depends on what what the computational model of your processing and memory design is. If it winds up, I mean, memory is naturally array structured. If it winds up turning into kind of regular self-similar decompositions of things in space and time over 2D grids, maybe it winds up in a weird way actually being an okay fit, but it might, it might not be a good fit at all. If you think of things like spatial architectures like FPGAs and CGRAs, we have had some success, but I still think it's a bit of a stretch, or it's not a great model for targeting everything that an FPGA and a CGRA can effectively do, but instead instantiating certain kind of design patterns that work well for the types of computational patterns that we target on those types of architectures. I'd say it's all right, but not an ideal fit. And then if you look at things like more complex coarse-grained computational units, functional units like systolic arrays and matrix processing units and stuff that are quite popular today. That's something where the general application domain that those are targeted for is a great fit. And the big question is what the right representations are for, I mean, any fine-grained programming language has a hard time targeting stuff where the fundamental units are so coarse and specific, because you basically have instead of having a traditional compilation problem, you have like a synthesis problem where you need to pattern match this really big, weird puzzle piece against many nodes of a program DAG simultaneously. I don't think halide exactly is a great fit for a TPU or something, but I think related ideas augmented with some specific structures that better capture coarse-grained, tile-wise, like systolic data flows and stuff. This is something else that we're working on at the moment in collaboration with people at Berkeley who are building accelerators like that. I think actually can be pretty effective.
Yeah, so to recapitulate, it's essentially, you really have to be sensitive to whatever the underlying hardware structures are. You
Exactly.
can't just say, we'll just adapt to some crazy thing. That seems too hard. Okay.
Yep.
All right, so last question from the audience, I think. So the question is the lifting from x86 binary code to halide sound?
No. So the reason I mentioned soundness in the next slide is because the synthesis-based technique is based on Alvin's whole approach of verified lifting. That first work that comes from dynamically tracing x86 binaries, which was a really cool project led by Tariq Mendes, who's going to be at UIUC soon, is definitely not sound. I actually honestly view that whole, so a lot of what I talked about is relatively applied research that's close to the edge or already across the edge of industrial application. I think a lot of this code lifting stuff is better thought of more in the regime of kind of more traditional blue sky academic research, where it's trying to push, it's not saying that this artifact that we built right now is a thing that hundreds or thousands of production engineers should be using tomorrow. It's instead exploring whether it's even possible to do things that seem on their face kind of crazy, hoping that compounding effort over 20 years will make it so that there are tools that people can actually just use productively at scale. I think the synthesis-based stuff in particular is in a somewhat more practical spot, but it still feels to me very much like applied ML was maybe 5 years ago. It still is in new areas today, where if you have a PhD student who's an expert in the techniques, like in this case, Maz Ahmad, who drove the more recent lifting work, they can go spend a year and build a practical thing for one class of problem. Just like, if you have an ML PhD, they can often, given a year, solve a new computer vision problem that's kind of around near the periphery of what's been done before. But having a shrink-wrapped thing that you could throw over the shelf to a random software engineer, I think, is still pretty far out of scope.
Yeah, that makes sense. Yeah, so I mean, I I love the whole like this seems impossible on its face. Let's try to do it anyway.
Yeah.
That's always a lot of fun and can be very productive. But just to step back a little bit from that question, I mean, what are your thoughts on doing this soundly? Do you think that it matters that much? Is it something that is, it's a very PL perspective to be like, is it sound? If it's not sound, I don't care.
I think it depends. I mean, I definitely think that's obviously a nice to have, right?
Sure.
And I actually argued in the context of the Photoshop modernization work that I think there's a framing of that problem that makes formal guarantees actually really important, which is that all the operators we were modernizing in Photoshop, these are all the basically all the operators on the layers palette for anybody who's opened Photoshop. Effectively, those are part of the file format definition. So if those change their result from one from one version of Photoshop to the next, you reopen an old document and it looks different. And I don't think people think that's okay. Like you saved something that you've done and you expect the same pixels to come out the next time you load it. In other contexts, I think that's a particularly stringent example for a visual computing problem. Often, in numerical programming generally, a lot of stuff we do in graphics, makes fast math assumptions, like getting identical bits out isn't necessarily the most useful bar. I think it depends on the context. But interestingly, what people often from outside often think, oh, graphics, who cares? Pixels can change as long as it looks okay. You think of things like that Photoshop example. It actually does matter that you get the same bits,
right?
Because it's it's part of the file format that has gone back 35 years. I think it also depends the scale at which you're applying this. If you're applying this as a tool to augment a few humans investing a lot of effort in you're trying to make them a bit more productive in hand translating stuff, and it's part of a whole big effort that already has testing infrastructure and so on to help, because the alternative was they were going to handwrite stuff, and that's definitely not sound without some additional proof augmentation. And they'd usually be doing testing and other stuff to support that. Then maybe soundness matters. Matters somewhat less. But I mean, I guess this gets to classic static versus dynamic PL people debate. If we have lots of testing and so on, maybe we don't care. Right. In practice, I think also if this reached its kind of ultimate apotheosis in 20 years, where we can just press a button and translate huge chunks of a 10 million line code base, I think soundness matters a ton more than it does if this is, a tool in the loop to increase the productivity of people doing a targeted manual translation effort on some narrow chunks of code.
Right. Yeah, that makes a lot of sense. Yeah, I mean, it's if you have a giant testing framework, then maybe all the important cases are dealt with and you're good to go.
Right.
But yeah, if you're essentially treating it as a black box, then there's a lot of risk.
Right.
So, all right, great. All right, so I think we'll wrap it up here. Thanks for staying on longer for questions.
Yeah, thank you.
And enjoyed your talk.
Thanks.
And thanks everybody out there